it in many ways, from point of view of geometry, from a D-module point of view. But in these two talks, we are focusing on the finiteness properties. And the talk will have 6 parts. After a short introduction, we will review some elementary definitions and basic facts in local cohomology theory. Then we will discuss about the finiteness problems. We will see what kind of problems are called finiteness problems in local cohomology. At the 4th part, we will review some generalizations of local cohomology. And in the 5th part, we will review derived category approach in the theory of local cohomology. And one of the finiteness problem is cofiniteness. At the end, we will review cofiniteness and results that are appeared in that area. So for introduction, local cohomology was introduced by Grothendieck about 6 decades ago. And after that, it grows very significantly, and now it has many applications in both algebraic geometry and commutative algebra. In very early the beginning of this theory, Grothendieck asked a question that I will tell you what is the question in the 3rd part. And that question was a starting point for what we now call finiteness problem in local cohomology. Then Honecker presented some more questions that nowadays this collection of questions are the main body of the theory of finiteness theory of local cohomology modules. Just some notations throughout this talk. R will be a commutative Noetherian ring with identity, and by M of R we mean the category of R modules and R homomorphisms, and A will be an ideal of R throughout, and also M will be an R module. So now we will review some definitions in local cohomology. The gamma A functor is defined in this way. It's a functor from the category of R modules to itself. For M, gamma of M is all elements in M that are annihilated by some power of A. And for having a functor, we should know how it will apply on a module, and also how it apply on a homomorphism. Here, morphisms are R homomorphisms. For every R homomorphism like this, gamma AF is F restriction to gamma AM, from gamma AM to gamma AN. Now we record some properties, elementary properties of this functor. The first one says that gamma A is a left exact functor. The second one says that gamma A is equal to gamma B for every ideal B that have the same radical as A. And the third one says that gamma A is somehow idempotent. That means that gamma A of M is the same as gamma A M. And also it says that gamma A of M over gamma A M is 0. And the fourth part says that for any injective R module I, gamma A of I is injective. This is very essential in the theory of local cohomology. And this is one of the points that we use the notarian's assumption. There is another theory of local cohomology for non-notarian rings that developed by people like Schenzel, Lippmann, and Greenlees. But here we restrict ourselves to notarian case. So we have this good result here, very useful one. Now we can define the local cohomology modules. For each non-negative integer I, we have one local cohomology functor, like this, from the category of R modules to itself, that is defined as the ith right-derived functor of gamma A. That means if this resolution is an injective resolution of M, then Hi of M is the ith homology of gamma A of I dot. And it means that you should first apply the functor gamma A over this on this complex. Then the ith homology of resulting complex will be the ith local cohomology of M with respect to I. So this is kernel of gamma A of di over image of gamma I di minus 1. Let's have an example here. Let P be a natural prime integer. Then take the ideal, the principal ideal PZ. Ith local cohomology of Z with respect to this ideal is Zp to infinity when I is 1 and 0 otherwise. It's easily can be verified. Now we record some elementary properties of local cohomology, which in the same way, although they are very elementary, but they are very important too. The first one says that the ith local cohomology is an R linear functor. What this means? It means that for any two R homomorphism F and G from M to N, and any scalar R in R, we have HAI of R F plus G is the same as R HI F plus HI G. This means this is the definition of R linearity. And the second says that there is a natural equivalence of functors. The zero local cohomology is the same as gamma A. This is because this is a general fact in homology that if you have a left exact functor, then its zero right functor is the same as the original functor. The third says that if 0, L, M, and 0 is an exact sequence of R homomorphisms, then we will have this long exact sequence of local cohomologies. The next result deals with the computation of local cohomology. The first part says that local cohomology can be computed as direct limit of some X modules, X of X I of R over A to N and M. This collection of modules in a natural way is a direct system of modules, and its direct limit is the same as ith local cohomology of M with respect to A. And the second one is the following. Let x1 up to xt be a generating set for the ideal A, and this complex be the Church complex of M with respect to sequence of elements. Then the I's local cohomology of M with respect to A is just the I's homology of the above complex. So this is very useful result because readily we can see that after T and before 0, we don't have any homology for that complex. So local cohomology can be non-zero just when I is greater or equal to 0 and less or equal to T. And the third one, establish a connection between local cohomology and its counterpart in algebraic geometry. Let X be the scheme of aspect of R and Y be the B of A. It means that the set of all primes that are containing A, and M tilde denote the shift associated to M on X. Then the I's local cohomology of M with respect to R is isomorphic to local cohomology of X of shift associated to M with support in Y. And you can find this as an exercise in Harshon book. So local cohomology that studied in committed algebra is a special case of cohomology of schemes that studied in algebraic geometry. Next, recall the definition of grade for a finitely generated R module N. The grade is the minimum of integers, non-negative integers, that X of R over A and N is non-zero. Next, I recall the definition of cohomological dimension of M with respect to A, which is defined as follows. It's the supremum of I's, the local cohomology, the I's local cohomology of M with respect to A is non-zero. So we have the following. For those results can be found in the interesting book by Sharp and Brodmann. So if you find some results here that I don't mention to the reference, all of them can be found in Brodmann and Sharp book. Let N be a finitely generated R module such that, sorry, this should be N here, not M. N is not equal to AN. Then the grade of N with respect to A is the infimum of I's that HI of N with respect to A is not zero. So the minimum place that local cohomology of N with respect to A is not zero is completely determined by this theorem. But for the supremum of places that local cohomology is not zero, the situation is not so easy. It's challenging. The next theorem, if M is A torsion, by A torsion we means that gamma A of M is M. Then gamma A of M is zero for all I positive. So for A torsion modules, we don't have positive local cohomology module. Sorry, please stop me if there is any question. I cannot see the chat box. Is there any question?
As of now, there is no question. Not as of now. We will stop you in case we see some.
Thank you. The second says that local cohomology of M I's local cohomology of M with respect to A is isomorphic to I's local cohomology of M over gamma AM with respect to A for all positive I. And local cohomology computed by using injective resolutions. So we have the third statement, which is trivial. Local cohomology is 0 behind injective dimension. The fourth is clear by what I said about the computation of local cohomology using check complex. If A can be generated by T elements, then local cohomology of M, I's local cohomology of M with respect to I is 0 for all I greater than T. The fifth part says that local cohomology of M with I's local cohomology of M with respect to A is 0 for I greater than dimension of M. So these parts dealing with the vanishing, and now we have two parts dealing with non-vanishing. The first one is Lichtenbaum-Hartshorne vanishing theorem. Let R and M be a local ring and N a finitely generated R module. The following are equivalent. Sorry, the last part. This is I said the vanishing result, but because it's an equivalence with the vanishing of local cohomology, so you can consider it another way as a non-vanishing. The local cohomology of N at the point dimension of N with respect to A is 0 if and only if for each prime ideal P of R completion that satisfying dimension of R over P is equal to dimension of N, we have dimension of R completion over A R completion plus P is positive. Very readily we can have this corollary. Cohomological dimension of A and M from these three parts, we can see that the cohomological dimension of A and M, which is the last point that local cohomology of M with respect to A is non-zero, should be less and equal of the minimum of these three integers: injective dimension of M, arithmetical rank of A, and dimension of M. For those who are not familiar with this arithmetic rank, I bring its definition here. Arithmetical rank of A is the minimum of integers n, non-negative integers n, such that radical of A is equal to radical of the ideal n element x1 up to xn in R can generate. So we have the first part. Since cohomological dimension is less than or equal to each of these three integers, it should be less than or equal to its minimum. And Grothendieck non-vanishing theorem can readily be deduced from the Lichtenbaum-Hartshorne theorem. Assume that R and M is a local ring and N is a non-zero finitely generated R module. Then cohomological dimension of M with respect to N is equal to dimension of N. Here, the condition B for ideal M instead of A can be readily satisfied. For ideal M, if we put M instead of A dimension of R completion over M R completion plus P is 0 always. So because we don't have this, this local cohomology of n with respect at the point dimension n with respect to m should be non-zero. But historically, first non-vanishing, Grothendieck non-vanishing has been established, and then Lichtenbaum-Harshon theorem. So historically, the vice versa is okay, true. Now I'm going to explain what is the finiteness problems in local cohomology. What type of problems are called finiteness problems? In 1962, Grothendieck asked the following question in his algebraic geometry seminar. Let n be a finitely generated module and I be an integer. He asked whether the module home of R over A and HI of n is finitely generated. 2 years later, Harshon gave a counterexample for this question. The example is this as the same are here. Let K be a field, and take R be this four-dimensional regular ring K of X and Y. Power series over U and B over the ring K of X and Y, and take A be the ideal generated by U and V, and P be the prime integer, prime ideal generated by this element XU plus YU, XV plus YU, and let N be R over P, which is finitely generated R module. Then the R module home of R over A, HA2 of N is not finitely generated. So by this example, Harshon showed that Grothendieck coefficient has a negative answer. In 1991, Honecker proposed these questions, this series of questions, which this type of problems are called finiteness problems in local cohomology theory. Let n be a finitely generated R module. The first question is the following: when are these local cohomologies are Artinian? The second, when are these local cohomologies are finitely generated? And the third, when are circle of these local cohomologies are finitely generated? And fourth, is the set of associated prime of these local cohomology modules are finite always? And the fifth, when are these local cohomology modules are eco-finite? Eco-finite is a notion that I should define. I will do it soon. And the sixth question was, when are the bus numbers of these local cohomology modules finite? These notions, Artinians being finitely generated and finiteness of bus number, are not independent of each other, and there are close connection between these notions. I will reveal these connections in a remark soon. But before that, I bring the definition of cofiniteness. It's supported in V of A, and X R I of R over A and L is finitely generated for all integer I, non-negative integer I. Just pay attention that for an R module N, being a torsion is this point. So now the promised remark that X be an R module. Assume that X is either finitely generated or Artinian, then circle of X is finitely generated. Circle of a module is the sum of all simple submodule of that module. So circle of X is the sum of all simple submodule of X. So if X is either finitely generated or Artinian, then its circle is finitely generated. And the second, the set of associated prime of X is finite. And the third, for any integer n and any prime ideal p, the nth Bose number of X with respect to p and also the nth Betty number of X with respect to p are finite. These three statements are true for if X is either finitely generated or Artinian. One can check it very easily. The part B says that if X is finitely generated and a torsion, then it is a cofinite. So this is also clear because when X is finitely generated, here I mentioned that being a torsion is the same as say that it's supported in the VAA. So the first part of the definition will satisfy. And since if we take a finitely generated module, clearly these X modules should be finitely generated. So from the definition, it's clear that if a module X is a torsion and finitely generated, then it should be a cofinite. Part C assume that X is a cofinite. Then we have these three assertions. The first one, if the set B of A intersection with the set of maximal ideals is finite, then circle of X is finite, regenerated. The second part says that the set of associated prime of X is finite. And the third part says that all for any prime ideal P and any integer n, non-negative integer n, the nth Bose number of X with respect to P and the nth Betty number of X with respect to P are finite. From this remark, one can see that why cofinite modules are so important. Cofinite modules is a class much bigger than the class of finitely generated modules and Artinian modules, and yet they enjoy the good properties of finitely generated modules and Artinian modules. We will see in the examples that very seldom local cohomology is local cohomology module is finitely generated or Artinian, but there are many examples that local cohomology modules are cofinite. So the notion of cofiniteness for local cohomology is very important. This is the reason that we devoted a section for cofiniteness. In example 3.1, we see that this module is not finitely generated. So by definition of cofiniteness, this provides a counterexample also for the fifth question. So here, local cohomology is not a cofinite. And also we saw in example 2.4 that the first local cohomology of Z with respect to PZ is Z to Z sub P to infinity. And this abelian group is not finitely generated. So this is another example that local cohomology are not always finitely generated. But also here, one is the top non-vanishing local cohomology for Z. So this example is an special case of the next result, which is due to Divaani Vahidi. The next results, I mean, lemma 3.7. But I will bring proof for Divaani and Vahidi result. But first, we need the following two results for that purpose. Theorem 3.5 says that if L, N, and L are two finitely generated R modules such that support of N is contained in support of L, then cohomological dimension of N with respect to A is less than or equal to cohomological dimension of L with respect to A. So module with bigger support have bigger cohomological dimension. And the second one is an elementary result in basic homological algebra. Let F be an R linear right exact covariant functor from the category of R modules, T should be R modules to R modules. Then for every finitely generated R module N, one has a natural R isomorphism like this. F of N is isomorphic to F of R tensored by N over R. Now we can bring a proof for this result. Let N be finitely generated. If cohomological dimension of N with respect to A is not zero, is bigger than zero, then local cohomology of N with respect to A in C is not finitely generated. So the top local, whenever the cohomological dimension is positive, the top local cohomology is not finitely generated. So by this lemma, we can have plenty of examples of non-finitely generated local cohomology modules. For its proof, suppose in contrary that this local cohomology is finitely generated, and we look for a contradiction. As this is not zero, we can have a prime in its support. Let P be a prime ideal in support of this local cohomology. It's clear that local support of local cohomology modules of N with respect to A is contained in support of N, and also is contained in V of A. So it's contained in the intersection of these two sets. So we assume that this local cohomology is finitely generated. Now using Nakayama lemma yields that the localization of this quotient at P is not zero. So in particular, the quotient itself shouldn't be zero. Set T as R over annihilator of N. Then by theorem that theorem 3.5, this is a right exact functor. Readily one can use 3.5 to see that is a right exact functor. So using lemma 3.6, we can have the following display of isomorphisms. HAC of n over an. One can see that it's the same as a local cohomology with respect to this ideal AT, the extension of A to T of the same module, but we write n over an as T tensor n over an over T. Using 3.6, we have this, that it's isomorphic to HATC of T tensor by n over an over T. And now at third row, we write down n over an as n tensor by T over AT over T. Then we use the lemma 3.6 again. Sorry, just we here use the associativity of tensor product. Here we use lemma 3.6 again. HAT of T tensor by n over T can be written in this way. And then instead of T tensor by n over T, we write n. And this is equal to this. And finally, we have these isomorphisms. So, but n over an is a torsion. Clearly, any element of this annihilated by A, so this is a torsion module. And by one of the results that I mentioned already, for a torsion modules, positive local cohomologies are 0. Sorry, here should be n over an. So HAI of n over an is 0 for all positive integer I. So here we have C is positive, H is local cohomology of n with respect to A at C over A HAC n is non-zero, but here we have that this should be 0. So we arrived at our desired contradiction. So regarding the questions that we already asked, we find many examples that local cohomology are not finitely generated. For not being Artinian also, it's quite simple to find examples. But for the fourth part, it's not easy to find an example of that the set of associated modules, associated terms of a local cohomology infinite. And the investigation on this question has a long story. The question was asked originally by Honecker, as I said, in '91 until the year 2000. Many authors proved that the answer is positive in many cases. There are many papers in this regard. Paper by Honecker and Schar, paper by Lubznik, paper by Bradman and Lashkari, and also a paper by Khashayarmanesh and Salarian. But at that year, Arang Singh presented an example to show that the answer to this question is not affirmative in general. After that, Katzman and also Singh and Swanson provide more examples. But the original example of Arang Singh is the following. Let R be this hypersurface. Then the associated prime of third local cohomology of R with respect to the ideal generated by X, Y, and Z is an infinite set. Because the example given in the Arang Singh example is the hypersurface, Lebesgue conjecture that yet the original question by Honecker has affirmative answer for regular rings. So he raised the following conjecture: let R be a regular ring. Then each local cohomology module, local cohomology modules of R with respect to an ideal A has finite many associated prime ideals. There isn't a counterexample to this up to now, and this conjecture is shown to be true in many cases. When the given regular ring is local and its characteristic is prime, it's shown by Honecker and Sharp that this conjecture is true. In the case that the regular ring is local and its characteristic is zero, its eco-characteristic zero, it's shown that, again, the conjecture is true by Lebesgue itself. And also Lebesgue showed that this conjecture is for regular rings of unmixed characteristic, but unramified unmixed characteristic is true again. So just the case that remains is in local case is the case that local regular rings that in mixed characteristic when they are ramified. Even in this case, there are some special cases that has proved that the conjecture is okay. So now in the fourth part, is there any question until now?
No, not so far.
Is it too fast or too slow? I don't know what his reactions to.
Well, no, I don't think it is too fast.
So I should.
We will. We'll have a question answers maybe at the end of your talk.
Oh, sure.
Yeah.
So please ask any question if you have it. I will stop before 5:30 because I want to have more time to ask questions. So in this section, I bring the definition of some generalizations of the local cohomology. The first one is due to Jürgen Herzog, but even before Herzog, this notion was appeared in a text by Grothendieck. Let M be another R module. The generalized local cohomology modules H, I, M, and N is defined in this way by direct limit of some X modules. This is one of the generalizations of local cohomology. And there's 3 more. The second generalization is as follows. Let B be another ideal of R, and we denote this set with W of A and B. First, define a functor gamma A and B on the category of R modules by setting gamma A B of M be those elements X and M such that their support are contained in this set W of A and B. Then we define gamma A and B of F for any R homomorphism F as the restriction of F to gamma A and B of M. Then the generalized local cohomology module of gamma H A and B of M at point I is defined as the ith right functor of this functor gamma A and B, and this definition is originally due to Takahashi, Ishiwaza, and Yoshino. If I'm correct, let's just check the third name. Yes, yes, Yoshizawa and Yoshino and Takahashi. The third generalization is as follows. Let phi be a directed poset. By a directed poset, I mean it's a partially ordered set, and for any 2 elements in phi, there is an element. For any 2 elements alpha and beta in phi, there is a third element gamma, such that both alpha and beta are less or equal to gamma. By a system of ideals phi, we mean a family of ideals of R, such that if alpha is bigger or equal than B, then alpha sub A is contained in alpha sub B. And for any alpha and beta in phi, there is a gamma in phi such that A sub gamma is contained in the multiplication of A sub alpha, A sub beta. Given a system of ideals phi, we can define gamma phi, functor gamma phi on the category of R modules by the following formula. Gamma of phi of M is the set of elements that annihilated by some ideal in phi. And as usual, gamma of phi F for an R homomorphism defined by restriction of F to gamma phi of M. Then the local cohomology with respect to phi is just right functor of this gamma phi for any integer I. So I can start from here, but maybe it's good to stop here because we can have enough time for answering possible questions.
Okay, thank you, Kamran. We are open for questions now. Mitsuhiro Miyazaki, can you ask your question, please?
Would you give me an essential example of the last directed poset definition of local cohomology? Example of that is different from the power of defined by powers of ideals.
Yeah, if for an ideal A, if we take phi to be the set of powers, natural powers of A, then readily one can see this that this phi is a system of ideals of R, and the ordinary local cohomology of M with respect to I is the same as local cohomology of M with respect to this phi. So this is also a generalization of ordinary local cohomology.
Yes, I see that this is a generalization. So I want to know an example that is essentially different from the usual local cohomology.
I mean, sure, it's
You take symbolic powers
can have
prime ideal. If you take symbolic powers of a fixed prime ideal, they satisfy these conditions.
Symbolic power, you mean?
Symbolic power, take a nth symbolic power.
Yes, for example, if you take symbolic power, or even you can take Frobenius power, you can have many different phi, but for these phi's, you don't have any differences between. If you take phi to be the symbolic power of an ideal A or a prime ideal P, local cohomology with respect to phi is the same as local cohomology with respect to P, because these two direct posets are cofinal. One can check that if two system of ideals be cofinal, then the local cohomology with respect to them are the same. But we can construct examples of local cohomology with respect to a phi that is not the same as local cohomology with respect to a single ideal. It's possible to find such examples. If you want to ask this.
Okay, thank you.
And maybe here is good to review that for any of these generalization. For the first one, the first generalization, if we take M to be R, then we recover the ordinary local cohomology. And if in the second generalization, if we take B to be 0, then again we recover the local cohomology with respect to A. And for third, as I said, if we take phi to be the set of all powers of a given ideal A, we can recover the ordinary local cohomology. So very easily, all of these three are generalization of ordinary local cohomology. In the next session, I will going to present a generalization that cover all of these generalizations.
I have a question about the finiteness of associated primes.
Please go ahead.
Yeah. So, of course, in general, the hypersurface constructed by Anurag Singh shows that the associated primes need not be finite.
Yes.
And if you take regular ring, then the associated primes of all the local cohomology modules with respect to any ideal are finite, right?
This is a conjecture. In many cases, this conjecture established. But yet, it's, for local case, for eco-characteristic case, is okay. For unmixed characteristic, when the ring is unramified, also it's okay. The only case for local regular rings that remain is the case that the ring is unmixed and ramified.
Okay. Yeah, but if you take characteristic P ring containing
yes, it's okay. It's done by Honecker and Schar. Yes.
Right. So one generalization of regular rings in characteristic P is the concept of F regular ring.
Yes.
All ideals are tightly closed. Do we have any information about associated primes in that case?
Yes, good question. Unfortunately, I don't hear about it, but it's good question. It's, yes.
Because that will enlarge the class because many rings of invariants are F regular.
Yes.
Yeah.
It's a good question, but I don't have any idea about that.
Okay. I mean, there are some papers about local cohomology of determinantal rings by Anurag Singh recently.
Yes.
But I don't think they consider the associated primes. Yeah. What about
there are some papers by Singh and Liebznig and two more people that they care about some smooth rings, but among other things, they show that the set of associated primes are finite. They care about the Liebznig conjecture, but also they have some other good results in their papers.
Yeah.
It's very recent. One can find it on archive.
Yeah. What about attached prime ideals?
For attached prime ideals, if it's very close to Lichtenbaum-Harshor theorem. In Lichtenbaum-Harshor theorem, it's deal with the local cohomology at the point dimension. It's determine whether it is I don't know. You see my slide or not?
Yeah.
In fact, in the situation of Lichtenbaum-Harshor theorem, the attached prime ideal of topolocal cohomology is all primes that dimension of R over dimension of R completion over AR completion plus P is 0. And so in this case, because this set is contained in the set of associated prime of the module, the attached prime is finite. And there are many other cases that attached primes are finite, but also one can readily find examples that attached prime is not finite. Of course, when one care about attached prime, should be careful that originally the attached prime ideals are defined for Artinian rings, Artinian modules, and in this situation, attached prime always is finite, because when you have Artinian module, attached primes corresponds to its minimal primary secondary representation, so it should be finite. But one should ask about the set of co-associated primes, and co-associated primes are not always finite. So we have cases in which the set of co-associated prime of local cohomology modules are finite, and also one can construct examples in which the set of co-associated primes of local cohomology is not finite.
Mm-hmm. Okay, thank you. Are there any other questions?
Can I ask a question?
Yeah, please.
Thank you, Dr. Kamran. You speak about three generalization of local cohomology. Is only this three generalizations are exist, or there are any? And is there a relation between these generalizations? Thank you.
Thank you for questions. Yes, there are more generalizations that in the on the Friday I will speak about them. And all generalizations that will be discussed here, we will present a generalization that cover all of them. I mean that the next session, I will define a generalization that all other generalizations are special case of that big generalization. But just one definition of local cohomology remains, that our big generalization and the second session will not cover it. There is a theory of local cohomology in compact derived categories by Benson, Krause, and Iyengar. That is in a different topic. It's completely in the theory of derived category, and problems like finiteness and things that we discuss in ordinary local cohomology and its generalization that discussed here cannot be reformulated at that definition. It's completely different. So we cover all existing generalizations of local cohomology, expect that defined by Benson, Krause, and Iyengar.
Thank you.
You're welcome.
Yeah, I guess I don't see any further questions, Kamran. So thank you very much for your nice talk, and we shall meet on Friday at the same time.